Okay, red light means we can go ahead and get started. Our question of the day last time had to do with other fields that you're interested in. Not surprising that math is high on the list. Math is very connected to computer science. Use lots of math. I want to spend just a couple of minutes on the document camera initially, and then we'll end with the document camera too. Let me make sure I'm looking at the same thing that you're looking at. So we got cut off at the very end last time. I was able to show you the traversals and talk about the fact that moving that print command would change it from a pre-order to an in-order to a post-order traversal. But there were some other things with that code that I just thought I would mention briefly. I had to have some code that would construct some kind of a tree, and the kind of tree that I was constructing there was one where you tell it how many nodes you want, and it just kind of numbers the nodes sequentially. So 1, and then kind of the next level, 2, 3, 4, 5, 6, 7, 8, 9. If there had been more, it would have been 10 and 11 and 12 and 13 and 14 and 15 and so forth. So it was just kind of, it constructed a tree. I don't know that this tree is useful for anything, but I needed to have something there, so that's what I did. It included a method that produced this output, and I wanted to just kind of mention what that is. It's being produced by a method that I called print sideways. It's kind of a crude visualization of the tree. You kind of have to turn it sideways, mentally, to understand that there's kind of a 1 here that's connected to these. These are connected here. These are connected here. These are connected here. This is connected here, and that's connected here. That's kind of what that tree looks like. So it's kind of showing you a way of visualizing the tree. Now, JGrasp has actually very nice visualization tools for binary trees, so you won't necessarily need something like this. But this is kind of a version you can use if you're interested that prints a tree in a sideways way. There were some funny things involved in doing that, like in printing. I want to have the right-hand subtree appearing first, because when you turn it sideways, the things that are going to be to the right are the things that are at the top of this output. But that meant that you'll notice, for example, that the recursive calls print the right-hand subtree first and print the left-hand subtree later, because that's how to get it to be in the right order for a sideways type way of looking at it. So I just kind of wanted to mention that. Maybe I'll also just briefly mention that it was interesting to write code that produced this kind of tree. I sometimes ask students, can you see a pattern here? Like, what's the relationship between this parent node and its 2 children here, or this parent node and its 2 children, or this parent node and its 2 children? And people are usually pretty good at spotting the fact that, if there's an n here, then what's here is 2n. And then what's here is 2n plus 1. So the tree has kind of a nice property to it that you can predict what the children store based on what the parent stores. And that led to a pretty simple code for constructing that tree. There's a build tree method here that makes left and right subtrees with 2n and 2n plus 1 as the values that are stored in those subtrees. And it has a test that basically says we tell it how many nodes we want, maximum number of nodes. In this case, it would have been 9. And if we're ever past something bigger than that, then we just give an empty tree. We stop building a tree, and otherwise we build with that simple rule of the 2n and the 2n plus 1. So anyway, that was kind of some code that I put on the calendar for Friday, but I hadn't yet explained. Let me switch back to the laptop for this next bit of stuff that we're going to do. And let me make sure we're looking at the same thing. So what I want to do next is we're going to continue our discussion of binary trees. Now that that sequential tree was kind of a stupid tree. Who wants this 1, 2, 3, 4, 5, kind of tree? Today we're going to look at a much more interesting tree that's known as a binary search tree. Now, the binary search tree has a property that's known as the binary search tree property. And this is kind of a way of describing the binary search tree property, that we have some root data n, for any given node of the tree. If there's kind of root data n here, then the values that are going to be in its left-hand subtree are all values less than or equal to n, and the values in the right-hand subtree are all values greater than n. So that's kind of a rule that we're going to impose on the entire tree structure. I have a little program set up that we can use to explore this. I normally ask the class for suggestions for characters out of a TV show or politicians' names or something like that. I don't have you guys to be able to do that. I decided I've watched a TV show called Schitt's Creek recently, which was a great show. I think it's one of the best shows I've ever seen. So I highly recommend it. If you haven't watched Schitt's Creek, I recommend it. But these are the top 10 names of characters from Schitt's Creek according to the IMDb page for that show. And this is a tool that Marty Stepp set up that lets me kind of put this into a randomized order. So let me go ahead. I've got a program here that builds up a binary search tree slowly but surely. You're going to be asked on the final exam to do this yourself. I'm going to give you a sequence of words or names, something like this, where I give you kind of a set of things, and I want you to show the binary search tree that would be generated if you added them in that order. So this says to add Twyla first, so I'm going to go ahead and do that. And there's nothing in the tree. So when you add Twyla, the only thing to do, this is an empty tree that we represent it with a null. The only thing to do is to replace that null with a node that's got Twyla in it. It's a little more interesting when we add Stevie. So Stevie is alphabetically less than Twyla, and so it would go to the left. That was that binary search tree property, that the things that are less than or equal to the root node go to the left. So Stevie's going to go to the left, and you'll see we add Stevie here off to the left. Jocelyn is next. Jocelyn is alphabetically less than Twyla, so we go left. Alphabetically less than Stevie, so we go left again. Patrick is kind of interesting. Actually, this tree is turning out to be what we would call a degenerate tree. It doesn't have as much branching as we'd like, but Patrick is alphabetically less than Twyla, alphabetically less than Stevie, alphabetically greater than Jocelyn. So we kind of went left, left, and then right. Ted is interesting. Okay, so Ted is alphabetically less than Twyla, so we go left. Alphabetically greater than Stevie, so we go to the right. So the Ted gets added there. David is alphabetically less than Twyla, so we go left. Alphabetically less than Stevie, so we go left. Alphabetically less than Jocelyn, so we go left and add David there. Alexis is going to be kind of similar. Less than Twyla, so left. Less than Stevie, less than Jocelyn, less than David, so ends up over here. Okay, Moira. So Moira is alphabetically less than Twyla, less than Stevie, but greater than Jocelyn, and less than Patrick, so it ends up over there. Roland is alphabetically less than Twyla, less than Stevie, greater than Jocelyn, and greater than Patrick, so it ends up over there. Johnny is less than Twyla, less than Stevie, greater than Jocelyn, less than Patrick, and less than Moira. And let's see what happens when we add Ronnie. Ronnie is less than Twyla, less than Stevie, greater than Jocelyn, greater than Patrick, and greater than Roland. So all of that's kind of interesting. The tree kind of got built up, and it never ended up having a certain thing that I was looking for. So what I'm going to do actually is I'm going to add a duplicate. So remember that with duplicates, the binary search tree said things that are less than or equal to. Well, let's take a look at that. Because actually, you do kind of have a choice that you could decide that you don't allow duplicates in a tree. What does that sound like? A structure that doesn't allow duplicates. Sets don't allow duplicates. And in fact, Java's built-in tree set is a binary search tree that forbids duplicates. So you could just say, I don't allow that. I don't allow you to put in a duplicate. All of the things are strictly less than n. I wanted to kind of allow duplicates in this case, but then you just have to decide, do they go to the left or they go to the right? And it could be either way as long as you're consistent. So here I've said that they should go to the left. So what I'm going to do is I'm going to add a duplicate of Ted, which means it's going to end up going to into the left-hand subtree. So I'm going to add Ted, that's a duplicate. So less than Twyla, greater than Stevie, and it goes to the left. Oop, it had to scooch things apart. So that was kind of something that I was looking for. When I have an audience, I always am hoping that the audience will kind of go, ooh, or something, that it does that little scooching thing apart. I wrote this program one night when I was thinking of something that would be useful to show to students the next day, and at 4 or 5 in the morning, it didn't do that scooching thing, and I was trying to decide, do I just stay up all night and get the scooching thing to work? And I decided, yeah, I'll just stay up all night. So it does the scooching thing if it needs to do the scooching thing in order to be able to display the tree. I'm going to post this to the calendar for today in case you wanted to play with this program yourself. It also lets you practice the traversals in case you wanted to do that. So you can ask it to do a pre-order traversal, and you can think about the sailboat approach. It would print while it's passing on the left, so it passes Twyla, it passes Stevie on the left, it passes Jocelyn on the left, then David, then Alexis. So it kind of goes through all of these different this sequence of things, so you can see whether you know how to do a pre-order traversal. You get some sequence of names. We can then do, say, an in-order traversal to make sure that we know how the in-order traversal works. Now, I want you to take a look at what we're getting here when we're doing this in-order traversal and see if you notice anything about this sequence of values that we have here. And so, again, usually I have the class who can answer that question, but probably you've noticed it's in alphabetical order. If you do an in-order traversal, you get them in alphabetical order. Well, that's because basically we are alphabetizing in the way in which we are building up this structure. So think about it. What does an in-order traversal do? It traverses the entire left-hand subtree, and then it traverses the root, and then it traverses the entire right-hand subtree. So if we're, say, printing, a sequence of values, it's going to print this data n after values that are less than or equal to n, and before values that are greater than n. So it's going to visit that node, it's going to, say, print that value at just the right point to have sortedness, to have it in sorted order. So a binary search tree is a very useful structure because, in effect, it's building up a sorted structure. It's building up a structure that captures the sortedness of what we have there. So that's a very useful aspect of the binary search tree. If any of you attended or watched the optional lecture on Quicksort, you may notice that this has a relationship to Quicksort. In Quicksort, we picked a pivot value, and we partitioned things into things that were less than or equal to the pivot and things that were greater than the pivot. And so the binary search tree is really like a structural parallel to Quicksort. It's doing the same kind of thing that Quicksort does by using some kind of a value, that here it's a value stored at the root, a pivoting value to kind of separate stuff into things that go to the left and things that go to the right, things that are less than or equal to n, things that are greater than n. So that's one of the reasons that we really like this structure, is because the in-order traversal gives it the values to us in sorted order. Well, I want us to kind of spend the rest of the time today figuring out how to create an equivalent structure using the int tree that I introduced last time. So this int tree program, so I was just showing you this code. This is that code that builds up the tree with the 2n plus 1 rule. And then here are our various traversals. There was the pre-order traversal we looked at, where you print first and then traverse the left tree and the right tree. There was the in-order traversal, where the print comes in the middle of the two recursive calls. And then there's the post-order traversal, where the printing comes after the two recursive calls. So that's kind of the code that we ended up with at the end of the last lecture. What I want us to do is to change it so that now we can build up a binary search tree of int values and use it to print those ints in sorted order. So I have a simple program here that constructs an empty tree, and then it prompts for a sequence of numbers, and you enter a 0 as a way to say that you're done entering values. If I try compiling it, the first thing it tells me is that I don't have a constructor that's a 0-argument constructor. Well, that's because what we did is we had this special constructor for making the sequential tree, where I told it how many nodes I wanted to have in the tree. Like the example I showed you, there were 9 nodes, so I passed in a max. Remember, the rule in Java is that Java will make a 0-argument constructor for you if there are no other constructors. But if you have even one constructor, then it assumes you know what you're doing, and that if you'd wanted a 0-argument constructor, you would have included it. Public int tree 0-argument constructor. It sees you doing this constructor, so it figures that if you wanted that, you would have included it. So we actually don't need to do anything, because all we really need to do is to set overall root to null to make it an empty tree. And that's actually what Java does for you, is it initializes the fields of an object when it constructs it. So it actually does that automatically for you. But it's not a bad idea to include it. It means that the constructor is not empty. We're being very clear that that's what's going on when we go to construct an empty tree. So that's what we're doing here, is we want to start with an empty tree. And if I try compiling this, now what it complains about is that we don't have the add method. Well, that's the whole point. That's what we're going to do today, is we're going to write that add method. So let me scooch down a little bit. We want to have a public void method called add that takes a value to add to the tree. You could think of this as being, so I told you the tree set, that Java's built-in tree set is a binary search tree, and it has an add method, right? Where we've used that before, add things to a set. So add a value to the structure. So we want to write code here that does the equivalent of what was happening over here. Now this was with strings, and it was putting the strings into alphabetical order, but otherwise it's the same idea. We're going to be dealing with ints over here, and we want to put them into sorted order, numerical order rather than alphabetical order. So I normally ask for suggestions about what to do. I get interesting kinds of suggestions, like people will sometimes say things like, well, if it's empty, then do a certain thing. And then one of the things that I would say in response to that is, if what is empty? So remember, we've got a tree here, and the tree has a field called overall root. So we could check and see whether overall root is null. So that would kind of take care of the initial case. Remember when we had nothing whatsoever and we added the Twyla node? So that we could kind of deal with that here. But how are we going to deal with all these other cases? To do that, we're going to want to write a method. We'll write it recursively. And you may remember last time in the lecture, I talked about this idea that there were 21 different trees that we wanted to be able to work with. And in order to be able to refer to the different trees, we needed to have an extra parameter. So, and I've said this to you, I said you might want to make a note of this, that every interesting binary tree method I'm going to ask you to write for homework or for the exam is going to involve having a public-private pair. So I'm going to have a private void add method that takes some parameters. And so remember then that you're going to have the ability to pick those parameters. And there was there were a couple of examples in the section problems from yesterday where you would have seen that that's important to be able to pick your parameter passing. It's even more true of the problems that we're going to be looking at tomorrow in section. So, this ability to be able to have the private method that has extra parameters turns out to be very important, and often the key to figuring out how to do one of these binary tree recursions is to figure out the parameter passing. So that's something to pay very close attention to. Here, I want to be able to have a way of saying something like add to the Jocelyn subtree. I want to be able to kind of say, make that the root that you're dealing with right now, or make this David node the root that you're dealing with right now. All of the different subtrees here, I want to be able to refer to any of them. And, this is kind of generally true, is that you almost always have a parameter of type int-tree node. I tend to call it root. Not always. There's, I think, at least one example tomorrow where you're building a tree, and so you don't take a root. But more often than not, in these binary tree problems, you have some existing tree. And so to be able to refer to different parts of the tree, you need that root parameter to be able to say this part of the tree or this part of the tree. And of course, we need to know what value to insert. We need those parameters. Maybe we need more, but actually it's going to turn out that that's all that we need. All right. Well, so what did we do in these different cases? Well, think about what happened when we added, for example, the Johnny node. So what we did is we descended the tree until we got to this node that had Moira in it, and at that point in time, its left-hand subtree was empty. So its left link would have the value null, and then we were inserting Johnny, and when we saw that that was null, we replaced the null with a reference to a leaf node. We introduced a brand new node, and we kind of changed that left link. Even in the initial case, if you think about the initial case, when we had no nodes at all and we added Twyla, what we ended up doing is we ended up changing the overall root. At that point in time, the overall root would be null, and we replaced that with a reference to a leaf node. At that point initially, remember Twyla was the only thing in the tree, that was a leaf node initially. So what I'm going to say here is that we should reach a point where we have a root that's null. So we're going to get to a point where we found that part of the tree is empty. Or it's the overall root, but when we get to a point where we found an empty tree, we want to replace that with a brand new int tree node that's got the value that we're trying to insert. So that's what we were doing over and over again, was we were finding the right spot, and that meant getting to a point where we had a null, and then changing the null to instead be a reference to a node. So that's kind of an important base case, is when we get to the appropriate spot, we replace the null that's there with a node. Otherwise, if something or other is true, and we'll think about that in a second, we add to the left, and else what we did was add to the right. Isn't that right? I mean, think about what is it that the question that I was asking over and over again, alphabetically less than Twyla, alphabetically greater than Stevie. So we were saying, does it belong to the left or does it belong to the right? And so we either went one direction or we went the other direction, And so that's kind of what we have left to do, is either going left or going right. So what would be the appropriate test there? Well, what were we asking when we started at Twyla, for example? I said, is it alphabetically less than Twyla? And so then we went to the left. And if it was alphabetically greater, turned out Twyla was an extreme case. There was nothing that was alphabetically greater than Twyla. But we had a little more branching, say, relative to the Jocelyn node. There were things that were alphabetically greater than Jocelyn that we ended up entering that went to the right. Well, remember the binary search tree property is that values that are less than or equal to the root data go to the left. So what property would we want value to have relative to the data that's stored at the root? It would be that if the value is less than or equal to root.data, then we add it to the left, and otherwise we add it to the right. So I'm just kind of taking directly from the binary search tree property. The things that belong on the left are the values that are less than or equal to the root data n. So, if the value we're inserting is less than or equal to root.data, it goes to the left, and otherwise it goes to the right. How do we add it to the left? Well, isn't that going to kind of depend on if root.left is null? Because if root.left is null, then we replace it. But what if root.left is not equal to null? Well, then that would mean that it goes to the left of the left. So we'd want to know if root.left.left is not equal to null. Because that's true of our tree here, is that root.left is not null, root.left.left is not null, root.left.left.left is not null. We have to go a long ways to find something, a place where we could do an insertion. Well, this is that bad way of thinking. This is going down that rabbit hole of non-recursive thinking. One thing that I try to keep in mind, I think it can be helpful to try to describe in English what it is that this method does. And you can kind of do it early, I think, as a way to make it a little bit easier to recognize where recursion is helpful. I mean, what I would say is something like inserts the given value into the subtree with given root so as to preserve the binary search tree property, something like that. So what is it that I want to do here? I've already looked to see whether it's an empty tree, and I've dealt with that case. So here I know it's not an empty tree. So I know it's my second kind of binary tree. Remember that my second kind of binary tree was a root node with left and right subtrees. So I have determined that this thing belongs in the left-hand subtree. What would I like to do? I'd like to add it to the left-hand subtree. If only there were a method that would allow me to add to the left-hand subtree this value, then I could just call it. I could just make a recursive call. I mentioned this last time, but it deserves repetition. When you pull the tree apart in this way, where you're kind of dealing with the root node, and then there's a left and a right subtree, because you're accounting for that root node, the subtrees have at least one fewer nodes than the overall tree, because you're dealing with that root. You're picking apart the tree relative to a root. So that means, if the overall tree had 10 nodes in it, we're dealing with one of those 10. There can't be more than 9 nodes in either of the subtrees. So the subtrees are smaller than the overall this tree that we're dealing with, that we were referring to by root. So that means that recursive calls should work. Leap of faith is justified. You can't keep reducing an int value over and over again and not get down to 0, not get down to an empty tree. So here we can say add it to the right-hand subtree, this value. So we either add to the left or we add to the right this value. Well, it turns out this isn't going to work. Some of you may know already that it's not going to work, and we'll talk about it in a second. But we're not quite done with it because we never said how to get the whole thing started. Well, what did we want to do initially? Initially, the reference we'd be dealing with is not some left or right link, but the overall root, the field that we use to keep track of the overall root. So we would have begun this whole process by saying add to the overall root this value. So add starting at the very top of the tree this value that we're trying to add. What I would say about this code is that it has a good logic to it. That, it kind of identifies the right kinds of cases. It's written in a way that we'd want to write it. But there is an important detail that prevents it from working. And that's what I want to spend the rest of the time talking about. Let me hit compile here. And then let me come over here and let's compile the client code. It does compile now because we have an add method. Let me go ahead and what if I added in a 5, a 2, a 15, 34, a -9, and then maybe we'll do a 0. So I've added a bunch of values to the tree, and it shows me the tree structure, and it says it's an empty tree, sorted list. What I'm doing here is an in-order traversal, so it should be showing me the values in an in-order way. Well, there's nothing in the tree. Everything is null. So it didn't work. So it didn't do anything. It didn't add anything to the tree at all. So that's what we need to talk about. So I want to explain something. This has to do with reference semantics. Remember, we've been talking about this all quarter, and I know you probably don't want to hear that again, that it has to do with reference semantics, but it's an important thing to understand. I'm going to do a non-binary tree example because the ideas that I'm going to talk about in this last 20 minutes is not particular to binary trees. It's something that applies to all of Java. I'm going to show you a certain technique that can be used in more than just the binary tree case. So, I'm going to bring it back to the binary tree case, but I want to make sure that you understand its general purpose, and maybe by showing it to you with a simpler thing, that'll make it a little easier to understand the issues involved. So what have I done here? I'm using the point class, which I've used, the book uses in chapter 8, the point objects, and we've been doing this for a long time, dealing with points. So what does this program do? It sets up a point object that X refers to, and it prints it out. It calls a method to change things. And that's going to be the big question, is kind of changes. What changes occur? And then it prints out what X is afterwards. Now, what happens in that change method? We have a parameter P that's being passed, and we translate the coordinates. So that's the first thing we do, is we use that parameter P to translate the coordinates. Then we change the value of that parameter P, and we print out what P is here. So I think that you can see what's going to happen inside of the change method. You probably can predict that fairly well. The big question is this one. What's that going to show? When we get back to main, because there are two different changes that I'm doing here, and which of these changes, if at all, are going to be visible when we go to print that point in main. You can place your bets if you want. Let me go ahead and compile and run this version of the code. And so we started out with our 2.8, in main, and then in our method we translated the coordinates, which turned it into 513. Then we reassigned P. But when we get back to main, notice that X is pointing at that node that has the 5 and the 13. So one of these changes took effect, one did not. And it's very important to understand that. So let me kind of draw some pictures here. I'm going to draw a crude ASCII art type picture. So what happens when you say X is assigned to a new point object? It sets up a variable X. We've been saying all along that means X is a reference to something. It's a reference to a point object that has an X coordinate of 2 and a Y coordinate of 8. Then what do? We print it out, and then we call change. And change is being passed X to a parameter called P. So it's as if we had done the line of code P is assigned to X. It's as if we had set P to be what X is. And what I've been saying all along is, P becomes a copy of X, but remember that X is an arrow. X is a reference. So that means that we copy the arrow. So let me try to draw this in a way that makes a bit of sense at least. I'm going to draw something that looks a little like an arrow. P is pointing at the point object that's got 2 and 8 in it. There's only one point object that we have here. Both of these variables, X and P, are referring to that one point object. So what is it that we're doing here? We're translating the coordinates. So using P, we go to that point, and we tell it to, remember this is a delta x and a delta y, change your x by 3, change your y by 5. So it adds 3 to the x coordinate, that becomes 5. It adds 5 to the y coordinate, that becomes 13. And we did it using p as the way of talking to this object, but it's as if we had used x, because they're both pointing at the same object. So 2 references to one object. I've made the analogy that it's like 2 of us, with the same phone number calling the same person. So there's only one person, that one object here that's being talked to, and 2 ways to kind of get to that object. So this is a case we are changing the state of an object. So using the reference to it, we change its state, okay? I think you can see, well, we saw it here with the output, right, at the very end, that x was 5 and y was 13. So this change worked. This change took effect. We were, having a reference to an object allows you to change its state. If you have someone's phone number, you can call them, and and they'll know you called them. You can tell them things, and they'll if you give me your friend's phone number and I call them, they'll say, "Why did you give Stuart Regis my phone number? He called me. It was very weird." Your friend will have changed their state. They'll be in a different state because I called them. So, since P has a reference to what X has a reference to, it can change the state of the object. But now what is it doing here? It's reassigning P to a brand new point object. So it goes and makes a brand new point object that has an X coordinate of -7 and a Y coordinate of -14, and it sets P to refer to that object. But notice that has no effect on X. We print out that P is referring to this object with a -7, -14, but when we come back to main, X is unchanged. So what we're trying to do here is not change the state of the object that we're referring to, but changing the reference to an object. So here we're trying to reassign, we are reassigning this variable P so that it's referring to a brand new object, a different object than it referred to before, but that has no effect on X. That has no effect on the parameter that we pass to X. So you can use a reference to talk to an object and change its state, but changing the reference to the object where you have a copy of that does not change the original. Like if you told me the phone number of your friend and I wrote it down somewhere and I changed what I had written down on my piece of paper, that doesn't change what you have in your phone. Well, not unless we wanted to do it on purpose. So I'm going to show you a technique. It turns out that if we were using C++ as a programming language, I'd explain to you that we're going to put a little ampersand right there, and suddenly it's going to change the original X. We're not working in C++, so that's not the way we're going to do it. But I'm going to kind of show you a way that we can do something very similar in Java. So suppose you really did want to change the original. It's as if, you give me your friend's phone number, and I'm going to give you back a phone number, and you're kind of having the option available that I can update what's in your phone. That's what we're trying to do here, is to kind of build in the option that this really does change what was passed as a parameter here. Well, so there's a value of this P that's in a local variable. The local variable is going away when the method is done executing. What did we learn in 142 about how do we get a value out of a method before the local variables go away? We would return it. So I'm going to say return P. Let me also point out that what I'm going to show you here is a very mechanical approach. I'm going to show you a technique where I am going to change the code in a very particular way. And you always do it the same way. I mean, it's kind of the mechanical change is kind of unambiguous. You don't have to understand anything about the code to know what it is we're doing with the change. We change the method so that it returns this thing, the reference that we're potentially changing. That means we need to change the return type. That would have to be a point. And we have to change it here because now, remember we talked about this a lot in 142, that now we have a method that's returning something back to main, but that's not going to have an effect on main unless we catch that value that's coming back to us and do something with it. In particular, we want to reassign x. We want to change x so that it takes on the value being returned by this method that had that was returning something back to us. So what happens in that case? Well, the p gets returned to main, and then that means that x is going to be reassigned so that it is pointing at p. You know, we copy this value of p into x. So the call on change x returns that brand new reference. We reassign x so that it has, you know, we set x to be p. We set x to have that same reference. This object, by the way, is kind of floating away. It's a helium balloon that kind of no one is holding on to anymore. And now x is referring to this object that's got the -7, -14. So if I compile and run this version of the program, now what I'm going to see is that it really did change the reference to x. Now x is referring to that brand new object that we constructed in the method. This is a technique that's very helpful. We're going to use it. We're going to apply it in the binary tree code in a second. And the TAs and I refer to this as x assign change x. It's a mechanical approach to changing Java code so that you have the ability to change a parameter. Well, over here, what was going on, we were being passed in a root, and we wanted to potentially change that root. We wanted to change it, and we want that change to be remembered. So in order to do that, we've got to follow that mechanical process. There were 3 steps involved. The first is that the method needs to return it. So we have to say return root because the value has to get back out of the method. The second thing we did was to change the return type, int tree node. And the third thing that we did was to change the call on the method. Now here there are 3 different calls on the method. Here we're calling it by passing in overall root, and we potentially want that to change. So if we're passing in overall root and we want it to change, it's going to pass back something, and we want to say overall root is assigned to add of overall root. Whatever is here, the thing that's potentially changing, should appear here. Well, there's a similar call on add here where I'm passing it root.left. So now it's root.left that's the thing that potentially I want to change. So x assign change x. Whatever x is here, here it's root.left. I'm going to say root.left is assigned to that. Here the x is root.right. And so I'm going to say root.right is assigned to that. So all that I did just now was to apply those 3 steps of changing this code into the x assign change x form. And if I now come back to my client code and run the code again, 32, 8, 5, 19, 7, -3, and then a 0, we end up with an interesting tree. And look, it's put it into sorted order. There's an in-order traversal of the tree. It worked. So now it works once we've made the change to put this into the x assign change x form. And that's what I meant before when I said that the logic was pretty good logic. We were approaching it the right way, but we needed the x assign change x ability to have the code actually work. This is something the TAs are going to discuss with you in the problems for tomorrow, because you often need to use the x assign change x approach in order to solve those harder problems. And you're going to need to do this on the 20-point final exam question and in both of the homeworks that are going to involve dealing with binary trees. All right, I want to do one more thing back on the document camera. So let me send that to the projector, and let me make sure I'm looking at the same thing that you're looking at. And so what I wanted to do was to talk about a specific case like this. So suppose that I have the value 12 as the root of a tree, and then I've got a value 8 over here, and I've got, say, a value 18 over here, and I've got a value 11 over here. So I've got my field called overall root that's referring to this node that has the 12 in it. And suppose that I have some, variable t that I'm using that keeps track of my int tree, and I tell it to add the value 10. So suppose that this is something that a client does. This is the current state of the tree, and the client says to add in a 10. I think you can see the 10 is going to belong down here, right? But what is it going to do? Well, I've got my add code here. This is the code that we were executing. And so what does it do? It calls the add method, passing in the overall root. So there's a first recursive call. And I imagine if I had people in the room, I'd kind of point at somebody and I'd say, you're the first recursive call, and you're going to have a parameter called root that initially is pointing at the overall root of this tree, because that's the initial call that we make, is that the first recursive robot is looking at the overall root of the tree. I'm going to kind of refer to that as root 1, because that's the root parameter of the first of these robots that's going to work on this problem. It says, well, that's not null. So it says, is the 10 that you're trying to insert less than or equal to the 12 that's here? And it is. So it makes a recursive call on root.left. So it makes a recursive call on this left-hand subtree. So we get a second robot involved, second recursive call. I'm going to call that root 2. That's passed the value 8. That's not a null. It says, is the 10 we're trying to insert less than or equal to the 8 that's here? No. So we go into the else branch, which is going to be passing in root.right. So a third robot comes into play that has a root parameter. I'm going to call it root 3, which is pointing at the right-hand subtree of this one. This one says, is my root null? No. Is the 10 that I'm trying to insert less than or equal to the 11 that's here at the root? And it is. So it makes a call on add, passing it root.left. So there's a fourth robot that comes into play that is passed a value. And what is it passed? What is root.left of this tree right here? It's null. So this fourth robot is passed a value null. And what does it do? It says if root is null. Well, root is null, because now we've gotten to the point, we found where it is we want to attach that node. So this one, this fourth robot, that's dealing with this problem, has a root value that's null. It makes a brand new node that's got a 10 in it, and it points at that node that has the 10 in it. So it reassigns its value root to point at this node that's got the 10 in it. But notice, if that's all that I did, this is not part of the tree. I haven't yet changed anything in the tree. But so then this is the really important part to understand, the mechanics of what's going on here, is that what does it do? It changed the value of root, and then it returns it. So it returns a reference to this brand new node that it did right here. And where were we? We had been here with this thing passing in the value of root.left. Root.left was null. Well, it's still null right now. But look at what we said here. We did the call on root.left. It's returning something new to us that we want to set root.left to be. So it's returning a reference to this node with the 10 in it, and we changed root.left so that it points at that brand new node with the 10 in it. This is when we're attaching that node. This is when an actual change occurs with the tree itself. So we return back to this node, the reference to the node we just made, and this one ends up replacing its null value with a reference to that node that just got constructed. Then what happens? Well, this one, there was a call on root.right. We passed in root.right, which was a reference to here. We're done now, so we return our root. And when we come back, we reassign root.right to be what's being returned. So we reassign this root.right to the reference to the node with the 11 in it. I mean, in effect, what we're doing is we're setting something to what it is already. It's like saying x equals x. It's a weird thing to say, but it's not a dangerous thing to say. It just sets something to what it is already. So we kind of overwrite this value here with what it is already. Then there'd been a call on root.left. We return from here and we reassign root.left to what it is already. And then this had been a call on overall root. We reassign overall root to what it is already. So as we come back up the tree, we do a series of assignments that in effect don't change anything because those parts of the tree didn't change. So only the lowest one, the last one, ends up making an actual change in the tree. As I said, the TAs will kind of give you their own explanation of this, but that's kind of the mechanics of what's going on to make x assign change x work for the binary tree.